Hello everyone, my name is Lisanne Verschuren and I'll be presenting about animal breeding towards the valuation of new feed. My company likes to remind me that I'm human and I can make mistakes, so please don't blame me for that. In 2019, it was ruled that the Dutch nitrogen legislation was in conflict with the European Habitats Directive. Construction work was halted, the maximum speed limit was changed to 100 km an hour, and it was suggested that livestock numbers should be decreased. Dutch farmers reacted to this by organizing a protest on the 1st of October 2019, and tractors flooded Den Haag. All of this because the nitrogen emission in the Netherlands exceeded maximum allowed levels from a legislation perspective. Nitrogen emissions could be decreased by geneticists and nutritionists collaborating within the pig industry. For geneticists, all pigs are different and differences in diets are a nuisance. Whereas for nutritionists, all diets are different and differences between pigs are a nuisance. Of course, there are differences between pigs and differences between diets. To understand the differences between pigs in nutritional efficiency, we're going to look at the biological processes involved. Nutrients in the feed are consumed by the pig and end up in the small intestine. There they are digested and partly absorbed. Nutrients that are not digested or absorbed end up in the large intestine, where they are partly fermented by microbiota. Fermentation products are absorbed across the intestinal wall. Nutrients that are not digested or fermented by the microbiota end up in the feces and leave the pig body. Digestion and fermentation products are absorbed across the intestinal wall and end up in the blood, where it is distributed across the body to several body tissues to either deposit protein or fat, or used in maintenance and heat production. Of course, these biological processes are partly under genetic control and might therefore have a genetic background. Pigs have a maximum capacity for protein deposition, and this is due to genetics and changes depending on age or body weight. If a pig consumes too much protein, then the protein will not be used for deposition, but will be used for energy production. In contrast, if a pig consumes too much energy and there is not sufficient protein to deposit, because protein deposition costs energy, then the extra energy not used for protein deposition, maintenance, or fasting heat production will actually be deposited in the form of fat. Hence, there is an optimum for protein and energy consumption through the diet for pigs. This graph shows the substantial variation in crude protein digestibility between approximately 100 pigs. On the x-axis, we see the average daily feed intake 5 days before slaughter, whereas on the y-axis, we see the crude protein digestibility in percentage on the day before slaughter. What we can see is that there is substantial variation ranging from approximately 60% to 85% of crude protein digestibility. In yellow, we see the values belonging to pigs fed a corn soy diet, whereas in brown, we see the values belonging to pigs fed a wheat barley diet. And what we clearly see is that the pigs fed a corn soy diet had a higher fecal crude protein digestibility than pigs fed a wheat barley diet. What we can also see in this graph is that the fecal nutrient digestibility decreased when the pig had a higher feed intake on the 5 days before measuring the crude protein digestibility. What we can also see is that female pigs have a higher digestibility of crude protein than male pigs, as the female pigs have triangles, whereas the male pigs have rounds. Deroux et al. Also looked into the variation in nutrient digestibility, and they found substantial variation in energy, nitrogen, and organic matter digestibility. They had a data set that was large enough to estimate heritability values for these digestibility coefficients and found that the heritability of all 3 tested digestibility coefficients was higher when pigs were fed a high fiber diet compared to a conventional diet. The genetic correlation between the estimates on the 2 diets were far below 1, but the genetic variation on the high fiber diet in the digestibility coefficients was so high that it would compensate for the low genetic correlation between the estimates. Hence, pigs should be fed a high fiber diet when estimating energy, nitrogen and organic matter digestibility coefficients if one wants to use these estimates for breeding, because the selecting the pig on a high fiber diet would result in more genetic progress, even though the commercial pigs might be fed a conventional diet. They also looked at the genetic correlation between energy, nitrogen and organic matter digestibility with feed conversion ratio, daily feed intake, average daily gain and residual feed intake. And they found that all 3 tested nutrient digestibilities have a negative genetic correlation with all 4 growth rates. This means that improving energy, nitrogen or organic matter nutrient digestibility by means of breeding will result in pigs with a lower feed conversion ratio, which is favorable. However, this will be achieved by decreasing the feed intake and the average daily gain, whereas the feed intake is decreased to a larger extent than the average daily gain, hence resulting in an improved feed conversion ratio. However, balanced breeding will be able to prevent the decrease in gain and daily feed intake if energy, nitrogen and organic matter are digestibility are traits to be selected for. Once nutrients are digested or fermented in the intestines and absorbed across the intestinal tissue, it ends up in the pig's body, where it can be used for growth, maintenance or heat production. An experiment by Carola van der Peet-Swering et al. In 2021 showed that there are differences between pigs in nitrogen efficiency. When pigs were fed 52 grams of nitrogen a day, 53% of the nitrogen on average stayed in the pig's body, whereas approximately 7% of the nitrogen left the body in the form of feces and 40% of the nitrogen left the body in the form of urine. However, there were differences between the pigs. Before the experiment, pigs were selected based on their breeding value for protein deposition. And during the experiment, it was shown that the pigs with a low breeding value for protein deposition had on average 50% nitrogen efficiency, whereas pigs with a high breeding value for protein deposition had 55% of nitrogen efficiency, so 55% of the nitrogen staying in the body. Of course, with genetic selection, we would go from low breeding value pigs to high breeding value pigs, and therefore increasing the total nitrogen efficiency of a population. Measuring nitrogen efficiency, as done by Carola van der Peet-Swering and her group, however, is very labor intensive and not easy to implement large scale in breeding programs. Hence, we try to estimate nitrogen efficiency using INRAPORC by measuring the daily feed intake of pigs and estimating feed intake and growth curves of these pigs. With those estimates, we could find a heritability for nitrogen efficiency of 22% in the starter phase, 27% in the grower phase, and 21% in the finisher phase. Nitrogen efficiency had overall a negative genetic correlation with average daily feed intake, but it also had a negative correlation with feed conversion ratio. Hence, selecting for nitrogen efficiency would decrease the average daily feed intake, but also decrease the feed conversion ratio, which is a good thing. Balanced breeding would be possible, and with that, the feed intake decrease due to selection for nitrogen efficiency could be balanced out. Apart from breeding for nutritional efficiency, there are other methods to improve the nutritional efficiency of pigs. One way is to group pigs based on their genetic potential. In an experiment from Carola van der Peetswering et al., it was shown that when pigs with a high breeding value for grower finisher performance or pigs with a low breeding value for grower finisher performance have differences in the total revenue in terms of money. What you can see in this graph is that in the end, it doesn't matter whether a high breeding value pig was fed a control or a more luxurious diet with higher protein content for the eventual benefit for the farmer in terms of money. However, when pigs with a low breeding value for grower finisher performance were fed a less luxurious diet, their performance on the balance was similar to when pigs were fed the control diet, whereas feeding those low breeding value pigs for grower finisher performance a more luxurious diet resulted in actually lower profits of these pigs. Hence, if we would group pigs based on the genetic potential, we could also feed the pigs differently and in the end of the day have a better profit for farmers. This is just one way to group pigs, but it is a perfect example of how nutritionists and geneticists in the pig breeding industry could help each other to improve the efficiency of the whole system. So, in conclusion, we can bridge the gap between genetics and nutrition by breeding for improved fecal nutrient digestibility and nitrogen efficiency, by grouping and feeding pigs based on the expected performance, and predicting grower finisher performance based on genetics, and also developing feeding strategies to express more genetic variation, like feeding pigs a more fibrous diet to express more of the nutrient digestibility variation. The research I talked about in this presentation, of course, was not just the work of me. We had a lot of collaborations with Wageningen University, INRAE in France, Schotters Feed Research, and of course my colleagues from Topigs Norsvin. Part of the work was funded by the European Feed a Gene project, which is already finished, and also by Breed for Food and the genetic partners in that project. I would like to thank you very much for your attention and take now any questions you have. Thank you.